The F-4U Corsair lay twisted in the jungle mud, its distinctive inverted gull wings bent but not broken. Marine pilot Lieutenant Robert M. Hansen had been forced down during a strafing run over Japanese positions. He survived. The aircraft did not escape intact. Within hours, Japanese ground crews swarmed the wreckage like ants on carrion. They had heard the stories. The aircraft the Americans called Whistling Death had claimed 2,140 enemy planes by war's end, more than any other Allied fighter. Its kill ratio was devastating, 11-1. But numbers meant nothing without understanding. Commander Minoru Genda, architect of the Pearl Harbor attack, stood before the wreckage with 4 engineers from Mitsubishi Heavy Industries. They had traveled 3 days through submarine-infested waters to reach this muddy crater. The Corsair represented everything Japan feared: American industrial might, technological superiority, and the changing tide of the Pacific War. Its Pratt & Whitney R-2800 double Wasp engine alone produced 2,000 horsepower, nearly double that of Japan's best fighters. "Disassemble everything," Genda ordered. "Every bolt, every rivet, every wire. We need to understand why we're losing." The engineers nodded. They had 6 weeks before Allied forces would likely recapture the island. 6 weeks to unlock the secrets of the most feared fighter in the Pacific. What they would discover would challenge everything Japanese aeronautical science believed possible. The Corsair didn't just break the rules of aviation. It rewrote them. The Chance Vought F-4U Corsair was born from desperation and ambition. In February 1938, the U.S. Navy issued a requirement that seemed impossible: a carrier-based fighter capable of exceeding 400 miles per hour. At the time, most carrier aircraft struggled to reach 300. Engineer Rex Beisel and his team at Chance Vought accepted the challenge with a radical design philosophy: build the smallest possible airframe around the largest available engine. The result defied conventional aesthetics. The inverted gull wing, bending downward from the fuselage before angling upward, allowed the massive 13-foot propeller to clear the deck while keeping the landing gear short and sturdy. The cockpit sat far back on the fuselage, giving pilots limited forward visibility. Navy test pilots initially rejected it as too dangerous for carrier operations. "It's a death trap," one commander wrote. The long nose made deck landings nearly impossible. The aircraft stalled unpredictably. Early prototypes killed 3 test pilots. But in combat, the Corsair became legend. Its top speed of 417 miles per hour made it faster than any Japanese fighter. The massive engine delivered a climb rate of 2,890 feet per minute. In a dive, it could exceed 450 miles per hour, speeds that tore wings off enemy aircraft. Marine pilots in the Solomon Islands named it Ensign Eliminator during training, but in combat called it the Angel of Okinawa. Japanese pilots called it Whistling Death for the distinctive sound its air intake made during high-speed dives. By mid-1943, the Corsair had proven itself. But Japanese intelligence couldn't understand how. On paper, the design violated fundamental principles of aerodynamics. The captured Corsair arrived at the Tachikawa Aircraft Research Institute outside Tokyo in August 1943. Chief engineer Jiro Horikoshi, designer of the legendary Zero fighter, assembled a team of Japan's finest aeronautical minds. They had studied captured P-40 Warhawks and even a B-17 bomber fragment. But the Corsair was different. It represented a quantum leap in aviation technology. The aircraft was transported in pieces, each component catalogued and photographed. The massive R-2800 engine alone weighed 2,360 pounds, more than some complete Japanese fighters. Engineers marveled at the precision manufacturing. Every rivet was perfectly flush. Every weld was immaculate. The aluminum alloy was lighter yet stronger than anything Japan could produce. One engineer ran his hand along the wing surface and felt only microscopic imperfections. Japanese aircraft of the era had visible rivets that disrupted airflow. But the true mystery lay in the wing design. Horikoshi stood before a blackboard covered in calculations, his chalk breaking under pressure. "According to our wind tunnel data, this wing configuration should create catastrophic turbulence at high speeds," he said. "The inverted gull design concentrates stress at the junction point. At 400 miles per hour, the wing should experience harmonic vibration leading to structural failure." Yet American pilots routinely exceed this speed. His team spent 3 weeks measuring every angle, every curve, every surface. They built a 1:4 scale model for wind tunnel testing. The results baffled them. The wing should fail. The mathematics were irrefutable. But somehow, the Americans had solved a problem Japanese science said was unsolvable. September 1943. The scale model entered the Tachikawa wind tunnel, a massive concrete chamber capable of generating 500 miles per hour winds. Engineers positioned high-speed cameras at 12 different angles. Pressure sensors dotted the model's surface like metal acne. Horikoshi watched through reinforced glass as wind speed increased. At 150 miles per hour, airflow behaved as predicted. Smooth laminar flow over the wings. At 250 miles per hour, minor turbulence appeared at the gull wing junction, acceptable within design parameters. At 350 miles per hour, something unexpected happened. The turbulence didn't increase. It decreased. "Stop," Horikoshi commanded. Engineers froze the test. "Run that sequence again. Slower this time." They repeated the test 5 times. Each time, the same impossible result. At high speeds, the inverted gull wing created a vortex that actually stabilized airflow rather than disrupting it. The downward angle forced air into a controlled spiral that reduced drag and increased lift efficiency. Japanese aeronautical theory had no framework for this phenomenon. "It's like the wing is teaching the air how to flow," one engineer whispered. They called it Yudu Ranryu, induced turbulence control. The Americans had discovered that controlled chaos was more efficient than perfect laminar flow. It violated everything taught in Japanese engineering schools. But the mystery deepened. The wind tunnel tests showed another anomaly. At angles of attack exceeding 30 degrees, where any normal aircraft would stall and fall from the sky, the Corsair model maintained lift. The thick wing root combined with the gull design created a pressure differential that defied calculation. Japanese fighters stalled at 18 degrees. The Corsair could practically hover. The Pratt & Whitney R-2800 Double Wasp was more than an engine. It was a masterpiece of American industrial engineering. 18 cylinders arranged in 2 rows, each producing 111 horsepower. Total output, 2,000 horsepower at takeoff, sustainable for extended periods. Japanese engineers disassembled it with surgical precision over 3 weeks. What they found was humbling. The cylinder walls were machined to tolerances of 0.001 inches. The supercharger, a device that forced compressed air into the engine for high-altitude performance, was more sophisticated than anything in Japanese inventory. The fuel injection system atomized gasoline into a perfect mist, maximizing combustion efficiency. Even the spark plugs were superior, using a platinum alloy Japan couldn't manufacture. Chief mechanic Takeo Shibata spent 14 hours examining the propeller reduction gearbox, a complex mechanism that allowed the massive propeller to spin at optimal speed while the engine ran at maximum RPM. "This single component required more precision machining than our entire Zero engine," he reported. The gearbox alone weighed 187 pounds and contained 73 individual parts, each manufactured to impossible standards. But the most devastating revelation came from materials analysis. The aluminum alloy used in the engine block had a tensile strength 40% higher than Japanese equivalents. The steel used in crankshafts could withstand temperatures 200 degrees higher. America's industrial base wasn't just larger, it was qualitatively superior. Japan could copy the design, but lacked the infrastructure to manufacture it. "We are not fighting pilots," Shibata concluded in his report. "We are fighting factories." October 1943. The research findings reached Imperial Naval Headquarters in Tokyo. Admiral Isoroku Yamamoto had been killed 4 months earlier, shot down by American P-38s in an operation based on decrypted communications. His replacement, Admiral Manaichi Koga, read the Corsair analysis with growing dread. The report was devastating. Japanese fighters couldn't match the Corsair in speed, climb rate, dive speed, or high-altitude performance. The Zero's advantage had always been maneuverability at low speeds. But American pilots had learned to avoid turning dogfights. They used boom and zoom tactics, diving from altitude, firing, then climbing away before Japanese pilots could react. The Corsair's speed made this tactic unstoppable. Combat reports confirmed the analysis. In the Solomon Islands, Marine Corsair squadrons were achieving kill ratios exceeding 10-1. Major Gregory "Pappy" Boyington's Black Sheep Squadron alone claimed 203 enemy aircraft destroyed in 84 days. Japanese ace pilots were dying. Men who had fought since Pearl Harbor, who had hundreds of hours of combat experience, were being shot from the sky by American pilots with only months of training. The tactical situation was irreversible. Japan had 1,500 trained fighter pilots remaining. America was producing 5,000 new pilots every month. Japan built 700 fighters in October 1943. America built 2,400. The Corsair wasn't just a superior aircraft. It was a symbol of America's industrial steamroller crushing Japanese hopes of victory. Koga authorized a desperate response: develop a new fighter to counter the Corsair, or modify existing designs to compete. But the engineering report was clear. Japan lacked the materials, manufacturing capability, and time. The war was already lost. The Japanese response was the Kawanishi N-1K J Shurden, codenamed George by Allied intelligence. Engineers incorporated lessons from the Corsair, a powerful 2,000 horsepower engine, automatic combat flaps that extended during sharp turns to maintain lift, and heavy armament, 420mm cannons compared to the Corsair's 6.50 caliber machine guns. The Shurden was Japan's most advanced fighter. In skilled hands, it could match the Corsair in turning combat and had superior firepower. Test pilot Saburo Sakai, Japan's surviving ace with 64 kills, flew the prototype and declared it the fighter we should have had in 1941. But reality undermined hope. Production began in January 1944. Manufacturing problems plagued the program. The landing gear was unreliable. The engine overheated. Quality control failures caused crashes. By March, only 50 had been produced. Meanwhile, Corsair production exceeded 700 per month. By war's end, 12,571 Corsairs would be built. Only 1,435 Shurdens ever flew. Worse, the Shurden arrived too late. Experienced Japanese pilots were dead. Replacement pilots had 100 flight hours before combat. American pilots received 300. Fuel shortages grounded aircraft. One Shurden squadron sat idle for 6 weeks awaiting gasoline. When fuel arrived, American submarines had destroyed the tankers carrying oil for the next month. The final insult came in February 1945. A Shurden squadron engaged Marine Corsairs over Iwo Jima. 4 Shurdens were shot down in 3 minutes. The remaining planes fled. American pilots reported the Japanese fighter was formidable but flown by novices. The technology gap had been closed. The experience and resource gap never would be. Behind the technical analysis lay a human tragedy. Japanese pilots knew they were outmatched. Lieutenant Yasuo Kuwahara, who flew a Zero against Corsairs in late 1944, described the psychological horror. We would see them coming, dark shapes diving from 20,000 feet. We would turn to engage. They would fire one burst and climb away. We couldn't catch them. We couldn't run. We could only wait to die. The Corsair killed some of Japan's finest pilots. Chief Petty Officer Hiroyoshi Nishizawa, Japan's second highest ace with 87 kills, was shot down by Corsairs in October 1944. Lieutenant Commander Tetsuzo Iwamoto, who survived 202 air battles, described the Corsair as death incarnate. He survived the war but lost 48 wingmen. American pilots respected their enemy but showed no mercy. First Lieutenant Kenneth Walsh, who shot down 21 Japanese aircraft, described a dogfight. I got on a Zero's tail at 15,000 feet. He tried everything: loops, rolls, split-S maneuvers. He was good. But the Corsair was better. I stayed with him down to 2,000 feet. One burst. He exploded. Walsh received the Medal of Honor. The Corsair also killed its own pilots. The tricky landing characteristics claimed 1,200 American aviators in training accidents. The aircraft stalled without warning. The long nose blocked forward visibility during approach. Pilots called the carrier landing checklist the survival prayer. But veterans loved it. Captain Robert Prescott, who flew 1,000 combat hours in Corsairs, said, It tried to kill you on the deck. But in combat, it kept you alive. By war's end, 2,140 Japanese aircraft had fallen to Corsairs. Nearly 9,000 Japanese pilots died. April 7, 1945. The battleship Yamato, pride of the Imperial Japanese Navy, steamed toward Okinawa on a suicide mission. She carried enough fuel for a one-way journey. The plan was simple: beach the ship and use her massive 18-inch guns as artillery until destroyed. It was desperation disguised as honor. American reconnaissance aircraft spotted the fleet at dawn. By noon, 280 American aircraft converged, including 84 Corsairs from carriers USS Essex, Bunker Hill, and Bennington. The Corsairs' mission: suppress anti-aircraft fire while dive bombers attacked. It was the largest carrier strike of the Pacific War. Lieutenant Commander John Bridgers led Corsair Squadron VF-9 in the first wave. They dove from 14,000 feet at 450 miles per hour. Yamato's anti-aircraft guns created a wall of steel. Tracers filled the sky like glowing rain. Bridgers fired his .50 caliber guns at the ship's superstructure, walking fire across gun positions. Explosions bloomed. Gunners died. The Corsairs made repeated strafing runs, drawing fire away from torpedo bombers. The noise was overwhelming: engine roar, gunfire, explosions blending into one continuous thunder. Yamato twisted desperately, but torpedoes found her. 1, 5, 10. Water poured into her hull. At 2:23 p.m., Yamato's magazines exploded. The ship disintegrated in a fireball visible for 100 miles. A mushroom cloud rose 20,000 feet. Of 2,778 crew members, only 269 survived. 4 American aircraft were lost. Not a single Corsair. The battle lasted 90 minutes. The age of the battleship died with Yamato. The age of carrier aviation, dominated by aircraft like the Corsair, had arrived. The Japanese engineers' study of the captured Corsair became classified after the war. Jiro Horikoshi, designer of the Zero, survived and wrote, "We learned that American success came not from a single brilliant design, but from a system. They created an aircraft that was difficult to fly but devastating in combat. They produced it in quantities we couldn't imagine. They trained pilots to exploit its strengths. We studied the machine. We should have studied the system." The Corsair served for decades after World War II. It fought in Korea, where it destroyed bridges, trains, and tanks in ground attack missions. The French used Corsairs in Algeria and Indochina. The final combat mission was flown in 1969 by Honduras against El Salvador, the last piston-engine fighter combat sortie in history. Of the 12,571 Corsairs built, fewer than 50 remain airworthy. Museums display them with reverence. Airshow crowds watch them fly with awe. The distinctive whistle of air through the supercharger intake still raises chills. Veterans who flew them are mostly gone now. The youngest would be 100 years old. But the lessons remain. The Corsair proved that unconventional design, backed by industrial might and tactical innovation, could change the course of war. Japanese engineers discovered that their enemy's strength wasn't just technological, it was systemic, cultural, and industrial. They were fighting not just an aircraft, but the entire might of American production. The inverted gull wings that defied Japanese calculations became a symbol. Sometimes, breaking the rules isn't recklessness. Sometimes, it's genius. The Corsair didn't just defy aerodynamics. It redefined them. And in doing so, it helped win a war and end an empire. The whistling death proved that in war, as in science, conventional wisdom is merely the wisdom we hold until something better comes along.